Welcome back to the second meeting of this workshop. If you don't know, it's a 4-week workshop. R is pretty complicated. We cannot really do this in 1.5 hours. What we did last time is we started with the introduction. So we talked about what R is. So that was kind of like the typical sales pitch. R is awesome, right? And then we talked about R Studio, which is the integrated development environment that we're going to use for R. It's separate from the R programming language, so you have to install both. And we did this last week. And R Studio looks kind of like this. And it should be installed on the machine that you have here. If you want to do this at home or in your office, then you need to install R Studio. Either somebody will help you, or the links to install R Studio are on the website here. If anybody wonders what the website link is, again, just send an email or catch me right after, and I will give you the URL or ask your neighbor, and they hopefully know it from last week. Does everybody know the link that I'm on right now? If not, then let me actually write it down here on the board for you. It is really small. It is michael.pastor.net. That's an R. And then what is it? It says, actually just go there. That's probably the easiest. So I will show you. That is my homepage. I hope people get there. Did you get it? You type in your URL michael.hasler.net. And then once you're there, then it's down says here, introduction to R programming, and that's actually the link. We will download some data from there, so you really need to be able to get to this page. Okay, here it has the introduction, and the last thing that we ended with last time was a homework, right? Who did homework? Workshops with homework. One brave person. I got an email, somebody tried and got disappointed. Oh, that was you, okay. Let's go really quick as a kind of like warm-up for what we do today through this homework and see what we're supposed to do. So it's in the slide set for introduction. That's what we did last time. All the way to the end. And then let's make it bigger. It has here 10 assignments. That's quite a lot of homework for one workshop. And let's start with it. The first one says it create a vector with 10 numbers, and the numbers that you're supposed to use are actually already given here. I will try to copy them so I don't have to type them. And go back to R Studio here. And what is the first thing that I told you should do with R Studio when you start a new project? You want to create a file that you put all your code in so that you can save the code that works for you and can use it later on. If you type it just in here, it's going to be maybe in the history up here for a while, but eventually it's going to be gone. And then tomorrow you wonder, what was the code that I put in to do X or Y? And that's kind of bad. So the first thing is you go to File, you say New File, R script, and you get this window here with an R script. And you probably want to already save it first so you know where it is. And there's a button called Save As. It's kind of like Word. And you can see here, I want to put it on my desktop. And I call it homework whw1.r. Then it has this name up here. And now I can write code in here. I paste what I got from before. Those are the numbers that I got from my slides. And what it asked me to do was, let's go back to this thing here. It says create a vector with 10 numbers and assign it to the name X. Okay, how would I do this? You need to give it a name, right? And then assignment operator in R, it's this funny arrow, right? And is that already good? Let's try. We can highlight this thing here and say run, and then it's going to get really executed. And then we get an error message. Thank you, R, right? The first thing that we do and we get an error message. Let's say what it says. It says error expected, comma in parentheses 3 comma, and that's really weird because there is a comma, right? So that's very upsetting. the answer to this is that R doesn't allow you to just like put a bunch of numbers, even with parentheses in there. You actually have to say what you want to do with those numbers. If you remember, I told you R is kind of like functional. It wants everything to be a function, and the function needs to have a name. And then in parentheses, you can put the argument. So we get a function name. And what we want to do is we want to combine all those numbers into a vector. And since in R we combine lots of things all the time, we came up with a very short function name, which is just C. Okay. Now all those red marks go away. That's pretty good. And then we can execute it. You can also hold the control key and push enter when you're in a line up here, and it will copy down here and execute it. And now it doesn't complain. And we can down here actually check what the value of x is. So let's try this. We just type x, and it says x has the values 3, 12, 6, -5, all the way to 7. And we get this extra 1 in parentheses here, but this is actually just a row number kind of. It's the index of the first element in the row. It's the idea that sometimes we have so many numbers, they don't fit in one row, and it's going to start over with the next row and the next row. And just to help us to keep those apart, it has this like row number or index of the first element of the row to the left. Okay, that's great. That wasn't hard. That's more just like a syntactical thing. You need to know, you need to use C to put those numbers together, and that R wants this assignment operator. Also, what we see is that here in the global environment, this X started to appear, and it says it has numbers 1 to 10. It kind of looks like this index thing down here, means that it has 10 elements starting with index 1 going to index 10, and it shows you a preview of what the numbers are. So we know right now R stores this information. Let's go now to the second one. It says, what is the data type of X, and how can we find out? You can look at this thing here, and it says num, and that probably means that it's numbers or something like that. You can also use a function. We will look at this later today. You can say, what is the class of X? And it will tell you, R calls this numeric. And that's the basic data type that R uses for almost everything. By default, if you type in a number, it thinks it's numeric, and it is really just a real number. Even though those numbers look like they are whole numbers or integers, but they're just rounded, and it doesn't display that actually it's 7.00000 and so forth. Okay, so it's numbers, that's great. There is other types of objects. For example, if I want to know what the class is of hello, in double quotation marks, then it says this is character, this is some text stuff. Okay, so far so good. Let's move on. Here it says, yes? Yes, then we will go through that. I think today that there is mode, storage mode, class, and it's super confusing, and we will talk about it. Okay. Then it says here, subtract 5 from elements of X. Let me actually copy this in here, and let me put this as a comment so that we know what to do. Maybe do this for the first one as well. Then I have already a solution sheet here. That's good. Said here, create this thing. And I put it back here. And it had more than one line. Okay, let's work on the second problem. Subtract 5 from the second, fourth, sixth, and so forth elements in X. Anybody try to think about this? How would you do this?
So the recycling property, I assigned it 0 and -5 to
so we can use tricky things like recycling. Let's do it first the stupid easy way. How about we just like find the second element, and what do? We subtract 5, and then we find the fourth element and subtract 5, and just do this. Let's first find the second element of X. For elements, you need to take the index operators, those are brackets, which basically reads as give me X sub 2 or give me X at position 2. This is position 1 of X. This would be position 2 of X. So we can execute this, and it finds the value 12, which lives at index 2 of this vector. And if we want to change this, we can just assign something to exactly that position. If I, for example, assign now the value 100, it's going to replace this value here with 100. Let's actually do this and see what happens if I execute this. then you see that all of a sudden this 12 here got erased and it's overwritten with a 100. That wasn't great, so let's change this back. And now it's 12, right? So if we want to add to this value, that's right now here, which I guess is 12, 5, then what we need to do is we need to look at the value, take the value, add 5, and put it back, right? And that's what we're going to do here. So we take the value of x at 2, which is 12, we add 5, and then we put it back to x2. And if we execute this, we will see it updates here to 17, because it added that. If I execute this line again, it will add another 5, right? But we don't want to do this. But we want to also do this to other positions. So probably a helpful thing would be copy and paste, which is always awesome. And I copied this a couple times, and we know that we need to do it with 4, and we know we need to do it, what did it say, with 6, and then we need to do it with 8. I guess it seems that it goes every even position, and we can execute those. And we see it updated all those numbers. We probably need to also do it with 10, but if we had a vector that's longer than 10, let's say 500, this is not a good solution, right? This is horrible. We need to copy and paste so much. So a better solution, there is probably like 20 of those. Programmers would say, oh, I need a loop, right? I need a for loop or whatever it is. In R, we're not big fans of loops, so we might not really do this. We might do things that are more tricky. One thing, what she suggested, is we could use recycling. We could actually make a vector that has the values 0 and 5, and add this vector to that vector. It will recycle and it will actually do exactly that. I'll show you really quick how that would work. That's probably the fastest way to do it, although very tricky. So let's use recycling. And so we could say x plus, what did we see? We make a new vector, we combine the values 0, so we add to the first element 0 because we didn't want to add 5, and for the second element we add 5. Since x has so many values and we created a vector of only 2, it would recycle. It would add 0, 5, 0, 5, 0, 5, and we can just execute this. Since I don't assign it to x, we just see the result here. It will make this vector 3, 17, 6, 0, 0, 13, and so forth. If we want to change x, we have to assign it back. And if we do this, then we see it updates the x up here. Okay, this is probably the most concise version, maybe not the most understandable. So probably in this comment, you would have to say, you know, I really want to add 5 to every every even element, and it's just easy to write it this way. But if you read this code, you will not understand what I really wanted to do. There's other options. I could also here as the index, I will not do this here, as the index use a vector of the values 2, 4, 6, 8, 2, 4, 6, 8. And I could actually pick several values as a vector, add 5 to only those, and put them back in the right position. So there's tons of ways to do this. Very, very exciting. Why do I punish you and trouble you with that? Well, all of those things, when I show you to make dashboards next week, are really important for you to be able to actually deal with the data before you can make those fancy graphs and put them into an interactive or like a static dashboard or an automatically generated report. Okay, so this was subtracting this. Compute the sum and the average of x. Well, of course, if you had a programming language, again, I do a loop, add them up and divide them. But in R, that's actually pretty simple, because if I want to do the sum of a vector, there's a function called sum, and it will just spit out what the sum is. And the average is called, in Excel, I guess it's called average. Here it's called mean, because the statisticians made this tool, and it says the mean of x of those values is 6.2. Good thing about those functions is it knows what to do with missing values and all those kinds of things and infinite values. So it will give you the appropriate answer for those things as well. Okay. Reversing something, we will actually talk about functions reversing later on. If you tried it, there's a function called rev, reverse, and you give it a vector and it will just reverse the order. Find all the negative values. That's, I guess, is interesting for us. So if we go back to the original values here, that's why I like this file here, because I can just go to a line and execute this line again, and it will fix my data here. So we have one negative value and another negative value. And how can we find that in our R programming language here. Find out which numbers are negative, and then let's do this as well. So this is my next two projects here. First doing this, and then doing this. So how would we find negative numbers? We only want to look at them, right? We don't want to change them, so we don't need to assign to x, but we could compare x with something. We could compare x with 0 and figure out, is it more or less than 0, and then it's probably negative or positive. And then we need to have some math specialist that tells me if 0 is a positive number or a negative number or not a number at all, I don't know. Wikipedia probably will help you, but let's try this. So I could compare x with 0, and I could, for example, ask, is x less than 0? Then I believe it's a negative number, and we can execute this, and what we get back is this vector down here. And it basically says false, 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 true, false, 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 true, false. What happens is, if I compare a vector with a number, it will compare each individual element. And then it will give me the answer in the same order as I have the numbers here. So we compare this with 0, say this is false, this is false, this is false. Hey, this is less than 0, so this is true. And we see that this has really true as this position, and then the second to last one is also negative, and you get a true here. Okay, so you get the answers just as a vector of, we last time talked about it, I think it's logical, as those Boolean values that say true or false. And now what would we want to do with that? We maybe want to know what positions are those in, right? And so what you can do is there's a function called which, and it tells you which positions have a true value. So I could take my x less than 0, put it in here, and execute it, and it tells me here the answer is 4 and 9, which means there is a true value in this vector at position 4 and at position 9. If I go up here, 1, 2, 3, 4 is a negative 1, 5, 6, 7, 8, 9 is a negative 1. So you can find the index, and then you can pick those numbers and do all kinds of things. What we now wanted to do here is, though, we want to remove all the negative numbers, and we have problems like that in our data often, where we get illegal values. For example, this variable is supposed to contain the age of people, and I find a negative number in there. What do I do? Lots of people would say, oh, remove the whole entry, right? That's probably a bad entry. But in R, you can actually get by with not removing a whole entry. That's, for example, the person that has a negative age, but just mark the age as missing, as we don't know what the real age of this person is because we got a number that wasn't a good number. So in this case, let's say negative numbers shouldn't be an X, and we want to set them first to an A and then remove them. Let's first set them to an A. So what I could do is I could actually ask where X is less than 0. So those are the ones that are problematic, right? And then I need to go into X and look exactly at this position. So I could, for example, do this, where I say, take now these true and false values here as an index into this and pick only the 4th element that has true and the 9th element. And if I do this, then it will pick only those, and it will say, you'll know the negative numbers were -5 and -10. And they are somewhere in this array. Now, since I am allowed to actually also assign to a subselection here, I can do really cool things. I can, for example, say this. I can say, please select all the negative numbers in X and assign them the value NA. And if I execute this, then we see up here, all the negative numbers are now missing numbers. If I calculate the average of this, it will tell me the average is NA. If I exclude the NAs, it will do the averaging correctly over all the other numbers in there. What they said is, they said, actually, I want to remove them, not just to set them to an A. How would I do this? Let me first fix my vector again, because I changed my vector here. Let me execute this row again, and I get the original numbers here. And now let's remove them. How would I remove those values? So I know I can get one value by just using an index, right? And if I want to get, let's say, 2 values like position 1 and position 2, I could do this, and I would get position 1 and 2, and I can choose whatever position I want here. Now what I can do is, interestingly in R, I can use negative indices. a negative index is a bad thing because lots of programming languages will start screaming and say, oh, you cannot have a negative index in an array. But R knows this as well, but it uses the negative sign as the hint that you actually want to remove elements. You don't want to select elements, but you want to select everything but those elements. So if I now say -1, 2, then it R thinks or knows that what I want is I want the whole vector X, but I want element 1 and 2 removed. So let's see if that really works. And now I got the values 6, 5, -5, 0, and we see that exactly the first two elements are removed because I have a minus sign. If I have no minus sign, it selects the first two elements. Now I can use this very conveniently because I can say things like this. I can say, I want to remove, actually, let me just copy it, exactly the result that this thing does. Because this thing says position 4 and 9 are the negative ones, and I want to remove those. So I can just take this, plug it in here, execute this, and then it doesn't work because it just selects the negative ones because I want to actually select all the ones that are not negative, right? So how do I fix this code? Tricky one. Several options. Right now, what I say, please select from X all the elements for which X is less than 0. But actually, I want to get rid of those. So I want to select only the elements that are more than 0, right? So that's one option. I could do this. And then we see, oh, now it's all the other numbers. I don't know, is 0 a positive number? Anybody good enough in math can tell me? I guess maybe it is, so probably we should actually write here greater equals to, and then we also get this 0 here. But I guess once you need to solve this problem, somebody will tell you if zeros are good for you or not. I guess for age, if this would be the age of people, is 0 a good age for a person? Anybody has kids, so you know, was a kid 0 at some point? I think for the first year, technically, it is less than 1 year old, so it's 0. So probably 0 is a good number. So we should include it, or you kind of run the risk that the babies are all removed from your vector. Okay, what are other options? Actually, the fun thing is I can get rid of this switch and it will still work. Gives me the same thing. And the difference is, if I do which, then I get index numbers, and R knows what to do with index numbers there. But R also allows you to use this kind of logical vector to subset and says, oh, if you subset with this, then I don't want to take this, I don't want to take this, I want to take this one, I want to take this one, and not all the other ones. So it's really, that's the same thing for our code here, if we see it with which or not. Okay. All you need to do is, when you have a problem like this, you Google, you find one of the solutions, and if it works for you, it's good enough, right? Maybe remember that there's 5 different ways to do it, and that might be also good. Let's do number 8 again, and then I leave the rest so that we have more time to work on new stuff today. So this is the next problem here. How long is X now? And I guess they mean after we remove all the negative numbers. So I probably need to change my X here, assign it, and we see now this X that's stored has the negative numbers removed. How do I find out how many numbers do I have left? Lots of people like to count, and I think in Excel you have a count, if, and all kinds of things. But usually, what if you have like an Excel sheet with people in there, like each row is a person? How do you find out how many people you have in your Excel sheet? Let's say it's a class list, and you want to know how many students do you have in your class in Excel. No Excel professionals here?
Just a control shift.
You go all the way to the bottom, you look at the line number, row number, and then say, oh, I know there's like, it says 80, but I know that my first row is actually the header, so it's probably 79 or something like that, right? Well, here we can do it with code, and since X is a vector, there is a built-in function, we'll talk more about it today, which is called length. And I can say, what is the length of X? And we'll say the length is 8. Also, you could have looked here, it says here, it goes from 1 to 8. So this is the highest index. So you see already here that you have 8 elements in there. Okay? So far, so good. So this is very basic. Today, we're still going to cover very basic, boring coding, programming stuff in R. And then I promise you next week is going to be great. We're going to be doing really awesome stuff. And I will just show you, we will end up hopefully with a dashboard that looks kind of like this, if it loads it, where it has like interactive graphs here, and you can find different Major League Baseball players here. Does anybody know the name of one? I don't care. Let's do all the catchers. Then it filters the catchers here, and you can do really, really cool stuff. And what makes me so excited about this, if I show you the R code, you're gonna get really scared because this is the R code that makes all of this. It places those three graphs in there, loads the data, presents them. So it's really, really, really easy. Once you get through the scary part that R has those function calls and you need to know what to plug into all those different things to do that. Okay, so spoiler alert, it's gonna be awesome, but not this week. Okay, so let's go to the painful stuff for this week. This week I wanna talk about objects and data. We already talked a lot about vectors and you use those brackets to find things in there, so we need to be a little more there, because where we wanna get is data frames. And data frames is kind of like the Excel sheet of R. And we want to know how to deal with those, and in order to get there, we need to do a little more. And the second part is functions and loops. I hopefully get through it somewhat today. The rest we're going to have to do next week. If you want to read up what this is all about, chapters 3 to 7 and 9 to 10 in an introduction to R. The chapters are really short. They're always like just like 1 page or 2 pages, so it's not as scary as it looks like. Talks exactly about what we're going to talk about this week. If you have issues remembering what we did last week, I couldn't do it, you can also go here, it says somewhere, go to an introduction to R and read chapters 1 and 2. And it has actually code examples and it's pretty self-explanatory. Okay, let's now go to objects and data. Okay, we have a long list of things to do. We have to go to look at attributes, then matrices, lists, all the way to the end, finally get to data frames. And the last thing that we do in this slide set is importing data, which is important for most of us because we probably already have an Excel sheet or some data that we downloaded from somewhere and we want to use it. And here we'll show you the kind of hints of what can go wrong if you download data somewhere. Okay, let's talk about objects. In R, everything is an object. So this vector x that we had is an object. If you just type one number and type enter, it's an object. It just doesn't have a name, and it goes away right away, but it is an object. And objects have attributes. And there's a bunch of intrinsic attributes. The two most important ones for us is mode and length. And let's first start with mode here. If we create this vector, in this case, I only make it with 3 numbers, then you can ask what the mode of this vector is, and it says numeric. And it just means that the data type, what you have in there is numbers, so it's numeric. If you want to change the data type, there's a whole bunch of so-called coercion functions, and they all start with as dot, and then whatever the mode or data type is that you want. For example, I could change the mode here to character, and then you see it gets double quotation marks. It's now not numbers anymore. You cannot do math with it anymore. It's text. And if you ask it for a mode, it says now you change the mode to character because you said you want to change the mode of X to character and so on in Y. So that's what you get. The modes that we typically deal with is numeric, logical. We already had logical. That's the true and false things. Character for text. And then if you want to do math and have complex numbers, there's a mode for complex numbers. It uses, or it can deal with complex numbers as a regular data type. And then it has a data type raw, and we're not gonna think about those. There's some other internal data types like pointers and stuff, but we don't need those either. Okay, the second attribute that all objects in R have is length. And we use this, right? I said you can type length X and it will tell you how many elements are in there. Here's another example. It has here 3 elements. If you say length X, it gives you 3. You can also make, interestingly, a vector that has no elements. You can say, I want to create a numeric vector, and it has no element. You could also put in here 1, 2, 3, and it would create a numeric vector with this number of elements, and they all would be, I guess, 0. Okay, so I create an empty vector here, and if I say E, then it says this weird thing. It's a numeric vector, really it is, but it has 0 elements, so it's not the number 0, it's just like really a vector of 0 length. If I ask it for length, it says 0. And then I can do really funny things. For example, I can go in this vector that has no elements and say, place at position 5, 12. Most programming languages will say, hey, this vector has 0 elements. You cannot place something in an index that doesn't exist. R actually extends the vector appropriately and says, you want to place something at position 5. Right now it has 0, so I have to make it into a vector with at least 5 positions, place the 12 in the last position. And since I don't know what the other values are, because nobody told me, I just put in missing values and say this is not available. Okay, this is awesome, but also a problem. If you, for example, are not aware that you're changing the length of a vector because the data that you read was read incorrectly, then you get really weird results and finding those will be painful. So be careful whenever you write something to a vector and the vector doesn't have that length, it expands the vector, and there will be a whole bunch of NAs in there, and if you don't think about that later on, you're going to be in trouble. You can also change the length of the vector by assigning to the length of it, to this function here, and then it will appropriately expand it and say, oh, you want 7 elements, I give you 7 elements, I don't know what's in here, so I give you a case. 12 was the only number that you gave me, so that's what we get. Okay, pretty cool. Nobody ever does those things here. Most people just like use a lens. Maybe sometimes people need an empty vector to start with and add 1 element at a time, but that's only if you do really programming. Okay, so those are intrinsic attributes. Every R object has them. Now there is also regular attributes, and they can be set by the user, or the people that implement the function will set some attributes, and you need to know how to look at them. Let's start here with the vector C, and I make a sequence from 1 to 4. And if I look at C, it says 1, 2, 3, 4, that's fine. And then I can look at the attributes of C and it says null. So it has intrinsic attributes, it has length and mode, because it's a vector. But when I ask it for regular attributes, it says, no, I don't have any regular attributes. I still can ask it for the length, I can still ask it for the mode, and you see for figuring out what data type it is, there's actually class, mode, and storage mode. And the reason why that is because R came from S, and they use different ideas about how to store things, and it's a big mess. Don't worry too much about it. I will show you how to deal with those. If you really must use something, the most healthy thing to use would actually be class. And we'll tell you this is integer. And that's probably one of the only places where R really creates integers and not numeric, not decimal numbers, when you use this way to write a sequence, because it thinks that you actually want to create indices and they should all be whole numbers. So it says, okay, those are integers. Doesn't really matter to us because if you start doing math with them, they will automatically be converted to whatever numbers you need. So don't worry too much about it. Okay, next one, attributes. And now it gets really creepy. I take my vector C and we had, what was it, 1, 2, 3, 4. And I set attributes. And this is the syntax way. I say, give me the attribute called dim in C. We know C doesn't have a dim attribute because on the slide before it said, hey, I don't have any attributes. Let's go back. Here it says attribute C is null. There is no attributes. So if I now set my dim attribute and I want to give it a vector with a value 2 and 2, and look at C, it changes completely how it looks like. Before it was a vector with the values 1, 2, 3, 4. Now it looks more like a table or a matrix. And that's really the only distinction between a vector and a matrix is an attribute of dimensions. If I tell you you have 2 rows, that's the first number here, and 2 columns, then it will just take the values in the vector and put them column-wise in here. 1, 2, 3, 4. Don't write this down, because there's way more comfortable ways and convenient ways to do this, but this is really what happens. A matrix is nothing else than a vector that knows I have a number of rows and columns. If I want to look at the attributes, it now says you set the attribute dim, so yes, you have an attribute dim with the values 2, 2. If I look at the length of this C, it says 4. Again, that is weird, because now you have a matrix with 2 rows and 2 columns, but it says the length is 4. Is length something that a matrix has? Probably not, but internally it's stored as a vector of length 4, and that's why R still tells you that. So be careful when you ask for the length of something, and it is some sort of table. It might not be very useful. Yes?
Does it 1, 2, 3, 4, 5, 3, 4?
No, it uses. I took this vector here. I made my vector. It's called 1, 2, 3, 4, right? See? And then I told it, hey, you have dimensions, and then it fills it column-wise. So it fills it first row, first column 1, second row, first column 2. So it fills it kind of like this by definition. Okay, then you can ask it for class mode and storage mode, and now it gets really funny because all three of those things say something completely different, right? It says, well, the class is matrix, and I think that's healthy to know it's a matrix. It says the mode is numeric and the storage mode is integer. So just, I hope we have it on the next slide, is very confusing. Avoid thinking too much about mode, storage mode, and class. Use class if you must, and what you really should be doing is you should use the function str for string representation of an R object, and that is the single most helpful function that you can have in R, to look at what data really looks like. For example, if we look at C, then it will tell us this. It will say, yes, there's integers in there. The dimensions of this system is, it has 2 dimensions, it has rows and columns, and my rows has 2, and my columns are also 2, and the data that's in there is this kind of vector 1, 2, 3, 4. So this is probably the healthiest way to look at it. You don't need to worry about mode, storage mode, and class unless you start thinking about changing the storage mode of those data sets. And we will use str a lot in this course and when you use R. Okay, now matrices, the easier way. Of course, setting those dim attributes is really arcane and like who wants to do this? There's a way easier way to do it. And there's a helper function called matrix. And I can tell you, please make a matrix with the values 1 through 6. I want n rows is 2, n columns is 3, and it will create this kind of system with the correct dimensions and everything, and it fills them again by columns. If you want to fill them by row, 1, 2, 3, 4, 5, you can say question mark matrix, and it will tell you, you can say by row is true, and it will do that as well. If you want to find an element in your matrix, then you use subsetting with rows and columns. So I need a row ID and a column ID, and then I will select a single element. So x22 will go to row 2, and then column 2, it will find element 4, and this is what you get. A single number that is the value that's stored in there. Also, you can select whole rows and whole columns by just leaving one of those indices empty. For example, I can say if x1 comma nothing, then it will select the whole first row, and you will get this as a vector. If you want to select the second column, you would say nothing comma 2, and nothing means select everything, and it will get you 3, 4, which is the column in the order first row, second row down here. So that's easy. We can look at the dimensions without figuring out that it has attributes and writing attributes and so forth. We can say, what is the dimensions of x? It says 2 and 2. What is the number of rows of x? It's 2. What's the number of columns of x? It's 3. And again, the length, it will say 6, because internally it will just give you how many values does the matrix contain, and it's just number of rows times number of columns. Okay, so far so good. So matrices are actually very easy to handle. What you probably need to remember is that you can look at dimensions of the matrix, and that you can select elements very similar to a vector here. Just that instead of having just one number, which is the index in a vector, you have now 2 numbers, which is a row index and a column index. I guess in Excel, how would you do this? You would say, oh, row 2 is B, I guess. Oh no, row 2 is 2 and column 2 is B, so you would say B2 or something. And that's the same thing, just with just numbers and a comma in between. Other than that, it's really the same. Okay. In R, as in Excel, we often want to give our columns names. And Excel now has this awesome table feature where you can actually give it names and sort it and so forth. For rows, it doesn't have names, but it would be very nice to have row names as well. And R supports both column names and row names, and has a function called column names and row names, and you can just set them. You need to be careful that I have exactly the same number of names here as I have rows, columns in my data set, and we'll just place them whenever I print the matrix next to the rows and next to the columns. And it will be very readable because now you have row names and column names. And other to regular Excel, R really knows this is not data, this is actually the name of the row, and this is not data, it's the name of the column. And once you do this, you can look at the dim names, and it will give you just a thing here, a data structure. We'll look at this later. I have 2 row names and I have 3 column names. You can also just say row names X, dim names, column names X, and you will get just like those names. So that's pretty nice because when you print it, you kind of like see what information is stored in there. but it's really cool because what you can now do is you can, let me see, do I have this here? Oh, I didn't put it here, but you can also use those to subset. You could, for example, say, I want to have the row that belongs to Michael, and I could actually say X bracket Michael, comma, and it would select the whole row. So you can then use this name instead of the numeric index, and that makes your life potentially a lot easier. Okay. What can we now do with this X matrix? We can ask it to sum up the rows. For example, here it says the row Michael sums up to 9, the row Peter sums up to 12. So it sums up those numbers. I guess this is 9 and this down here for Peter is 12. I can sum up columns. I will say column X1 has a sum 3 and so forth. I can get the average for each column. I can get the average for each row. And those are pretty convenient things that you probably want to do in Excel as well, right? Where you go at the end of some table and say, I want the average of everything in there. The R version is this column means here, and you get a vector for each column 1 element here. And what it internally does, and we'll talk more about this later or next time, is it uses a function called apply. And a function that's called apply takes a matrix and then applies a function to the rows or to the columns. And unfortunately, they use a very, very old way to specify rows or columns. They call it the margin. That's fine. But they specify that 1 is rows and 2 is columns. So you cannot just say margin is rows. It will not accept that, which would be awesome if it would. You have to know it's 1. And the idea why it's 1 is because whenever you write an index, the first index is the row index and the second index is the column index, and that's why they want this here. So this applies as you take a matrix X, apply something to all the rows, and what you apply to the rows is a function, and I want to apply the function mean. And it gives you then for each row one value, which is the mean of all the elements that were in here. So the mean of row Michael is 3, the mean of row Peter is 4. And since we do this so much with matrices, there is this column means, row means function, which does exactly the same thing. And whenever you say row means in R, this is what it does. It says, oh, I need to take the matrix and I need to apply the mean function to each row. And that's really what I want. Sometimes you can come up with more complicated functions here. For example, what if I want the median? And it would just say, please give me the median of each row. What if I want the minimum? Then it would just say minimum here, maximum, whatever you want to apply to a whole row. If you want to apply it to the column, you just say margin is 2, and it will give you the same thing for the column. So that's very helpful for lots of things that we want to do with this matrix. You can bind matrices together. We don't have so much time, so I don't want to go into detail too much here, but what you can do is you can say R bind for binding rows and C binds for binding columns, and it basically just takes 2 matrices and puts them together either on top of each other. That's a row bind. It binds the rows of one column to the rows of another column. Or column binds, then it just adds more columns there, but it's not really, for most of the things that we want to do, necessary. As is matrix algebra, we don't really do that and can skip here. If you want more, look at the slides. It's really straight out of the math book, how you do a cross product and things like that. Okay, now something that we're going to use a lot in R, which is called a list. So a vector has in the elements, and they're all of the same data type. They're all numbers, so all characters. They have to be the same. I cannot have a vector that has a number and then some text and then a picture or whatever it is. So I need a data structure for this. And the data structure for that in R is called a list. And a list can have different elements, and each element can have its own data type. And this is unfortunately very small because I have to get lots on my slide here. So what it says up here, let me read it from the screen. It's easier for me. It says here, LST gets assigned a list, and this is the constructor for list. And the list's first element is called name, and it gets the string Fred. The next one is called wife. It gets the name Mary. Then the next one is no.children, number of children, gets the value 3, which is a number. And then it says here the age of the children is not just a single number because they have 3, but it's actually 3 values. It's a vector of length 3 with 4, 7, and 9. And since it's a list, I can actually store this. The first thing has a data type. It's a single string, right? Text. The second one has text. The third one has numbers. And the last one has actually a whole set of numbers. It's a vector of 3 elements. And you can do this in a list because the list is literally what you write on a piece of paper. You can say, my first thing to do is this, my second thing to do is that, and so forth. You can put in there what you want. And if you ask it what this list contains, you get this structure here. It starts with a $sign and then the name of the element, and then what's stored in there. And there's Fred. So it says your dollar name is Fred, dollar wife is Mary, dollar number of children is 3, and dollar children age is this whole vector with 3 elements. And there is now 2 ways you can access this list. For example, if you know that you want to have the second element of the list, which would be this one here, this first element, second element, then you could use an index similar like a vector and say, I want position 2. But since it's not a vector but a list, you need to use those double braces here. And that's kind of confusing initially. Why do you need that? But the answer is just you need it. Otherwise, you will get as the answer again a list, which is a sub-list of this one. That's not what you want. So you can get element 2 and it will spit out that's Mary. Since lots of people want to use their names a lot because they see I have a list and I know I really want the wife element. And I don't care. I don't know, is it position 2? Is it position 1 or 15? Might be very tricky. So often people use this to say, give me a list, then the dollar symbol, and then the name of the element. So it says your list of a wife, and it will find the name wife, and it will spit out Mary. That's what you see a lot. And it even auto-completes here, because if you say list $W, it will still find wife if there's nothing else that starts with W, and it will auto-complete that. That's very convenient. Also, if you use R, I don't know if I told you before, RStudio and R, the tab key is really, really important. It's the auto-completion. You start typing something, for example, the name of a variable, hit tab and see what happens. You write the name of a function, for example, you know you want something that starts with M, like mean or median, type M and hit tab. It will tell you what kind of functions are in R that start with M, and it's very, very helpful to do. We will look at this when I start R again. Okay, here, so we can do this, and of course you can use str, which I told you before is a really powerful thing. You can see str, lst, and it will tell you it's a list with 4 elements. The first element is name, it's a character. An example is Fred. Second one is wife is character. Number of children is number 3. Number of children ages is a vector with 3 elements, and it gives you really the structure of this whole this kind of this information just like condensed. Okay, so that's pretty good. Let's now go to data frames where we really wanted to go initially, because data frames are the spreadsheets of R. And for data frames, in order to understand them, we need to know how vectors work. We did that at the beginning, right, last time and today. And you need to know how lists work. And that's why I built up the whole way to the list. And we need to understand data frames are not matrices. That's why we talked about matrices as well. Let's first start with why they are not data matrices. A matrix, like a vector, has to have the same type of data in each element. If you think about a matrix in math, there's all the numbers in there, right? There cannot be text in there. It's all numbers. Same thing in R, but often in an Excel sheet, you want one column that has numbers, maybe the age of somebody, one column that has text, that's the name of the person, one column that has maybe a date for the date of birth, one column that has something else, right? So that doesn't fit in a matrix, because a matrix says, no, they all have to be numbers, or they all have to be text if you allow matrices of text. So we need a structure that's flexible enough for a spreadsheet, and this data frame is exactly that. It is basically a matrix-like structure that can have a different data type for each column. And the way that it's implemented is, it implements it as a list of vectors, and each vector is a column. So it kind of like takes the columns and puts them in a list and says, my first element of the list is my first column, my second element of the list is my second column. And since lists can have different data types for each element, now my data frame can have different data types for each of my columns. So how do we do this? There's a constructor again, it's called data.frame, and then you say, my first column is called name, and it has the element Michael, Mark, Maggie. My second element is called children, and it has the values 2, 0, and 2, which are numbers. And if you do this and look at it, it will make this really like an Excel sheet. It will give it column names, row names. Since we don't have row names here, it will use 1, 2, 3, and it will put it into this kind of Excel sheet type structure. And hopefully it lets me copy this. I guess it does. And let's go back to RStudio. And let's look at how this looks like. If I paste it in here, I hope it did that in a good way. It creates this data frame. I say data frame, and we see we get the structure here. And the cool thing is here in the environment, this data frame pops up, of course, because I made it into, I gave it a name, right, data frame. And it has this kind of spreadsheet symbol next to here. It says there's 3 observations and 2 variables. Observations are rows and variables are columns. And if I click on it, it opens it up and it almost looks like an Excel sheet, right? It's just to look at, but you could sort it here by a number of children or by the name, but you cannot change anything in there. It's really just to look at the spreadsheet, but it's pretty good to like look at the data that you have. Okay, so this is our data frame. There's now, unfortunately, lots of things happening in our data frame. One thing that you should remember, it is a list. If it's a list, then you can use all the syntax that we had for the list before. So you could, for example, select a column by using the $sign. So I could, for example, select all the names by saying df $name, and I would get all the values in my column name, right? So Michael, Mark, and Maggie. But down here you see something weird happens. It's not just names, it's not just the text, but it tells me, oh, there's levels, and the levels are Maggie, Mark, and Michael. They're not even in the same order. What happens is that data frames believe that what you have is kind of like the answers to a questionnaire or something, where one question might be, what is your gender? And you can say sex and female. And then it says, it's really stupid if I have 5,000 people to store the word male and the word female 5,000 times. Let me make it easier. Let me make a lookup table and code this as numbers. And this is really what it did. It says here, this is a factor. Lookup table says the 3 names that I have is Maggie, Mark, and Michael. And really stored in here, although it shows the name, is just a number, which for now is not a big issue. But once we start doing something with it and say, is this, for example, the first element that text Michael, then it might say no, because it's a number string, but it doesn't show it to us. So this is very, very strange. So be careful with data frames. Once you put text in data frames, it often automatically converts it into this kind of like lookup table thingy. And if you get issues, think back about this. Google data frame, strings or character, and somebody will explain to you and say, oh, this is what happens. Okay. So we have this. We can also, for example, use matrix notation. You can say, give me from the data frame the first row in all the columns. You will get this kind of thing. Or you can use string data frame, and it will tell you, I'm a data frame, I have 3 observations, 2 variables. My name is this weird factor with 3 levels, and my children are just numbers. Okay? So now, once we have this, we can really start working with data the way we're used to in R. Last thing, I'm going to skip this, but in R, there's not just built-in objects like the ones that we talked about now, but there's user-defined objects as well, and they're called S3 objects. And all they really have is they have a special attribute that's called class, and then R uses this attribute in order to show you the data differently or plot it differently, or knows what functions go with this kind of object, but we don't have so much time, so I want to skip this and go to something that makes us more makes the knowledge that we already have more useful, which is reading in data that we want to do all those things with, right? Cleaning ages and getting rid of the negative ones, putting them in a data frame, finding different groups in our data frames and so forth. So how do we read data in R? The first thing is R comes with data sets, and different packages, extension packages that you can install can have data sets. Usually they're small, really clean data sets to just show you how things work. And the function to get a data set is called data. And one data set that's built into R is the iris data set. It has 150 flowers of different species or subspecies of the iris family, and it has different measurements. And so I can say I want to use the iris data set, so I say data iris, and that will load the data set. And then iris exists, and I can, for example, say here head iris. And iris is actually stored as a data frame. When we say store iris, it really says this is a data frame. And the function head for data frames looks at the first few rows, because often you want to just see, oh, what is the structure of this data? What kind of columns do I expect? But I don't want to look at all the 150 flowers or thousands of whatever entries. So it will, by default, give you the first 6 rows here. It will give you the headers. It says those flowers are described by 2 different lengths and 2 different widths. and a species column. And you see those are numbers, and this is text, so it's probably not a matrix, but a data frame, and we see really it's stored as a data frame. Doesn't really matter what those measurements are. Those are like leaf lengths and whatever. Some biology major was bored and like started measuring different things on flowers. Okay. One thing that's cool for data frames is there's a function called summary, which will look at each column and give you a summary for each column, because each column represents some variable, could be the age of a person, in this case the measurement for a flower, and it will look at summary statistics. If you have numbers, it will give you minimum, maximum, median, mean, first quartile, third quartile in there. If you have something that's not a number, it will give you things like this, like a count. It says there were 50 setosa, 50 versicolor, and 50 virginica. Those are those 3 subspecies of different flowers in there. So that's pretty good, because when you load a data set, the first thing that you should do is figure out, did I load it correctly, or did it get all mangled up when I load it? Sometimes in Excel, when you open a data set that's not an Excel sheet, it comes out, everything is in one column and just swooshed together. So you need to first make sure that that's not the case. So here's not the case, because this data set is really clean, it's built into R. But how does this work if we do this with a data set that does not come with R? And what I want to do is I want to show you how to import Excel files, because that's probably the most usual use case, right? That somebody has an Excel file, workbook, and wants to import something. Importing Excel files does not come standard with R. You have to install a package to do this, and it says here you need to install the package called XLSX, and I will show you how to do this. Hopefully I'm allowed to install stuff on this computer. So you have to go to Tools, Install Package, and then just start typing. And then it says if I type Excel, then there's all those packages, and I think this is the one that I want, XLSX. And then it says installing that, and hopefully lets me do it. I guess it does. It's very happy about all those things. Installs more, installs manual pages. Almost done, hopefully. Oh, and then it says error. What does it do? Installation had non-zero. Oh, it doesn't let me install Java on this machine. On your machine, hopefully your administrator will let you do those things. And then if you do this, then you can actually just say something like this. You say XLS, read XLSX2, give it a name, and then you have to give it a sheet index, because you know workbooks in Excel have several sheets, and you need to tell it which one, because our data frame is only one table and it cannot handle several tables. So in this case, I read the index sheet 1, and I got this kind of data. I will show you the data though that I started reading from. And it is this was the wrong button here. Down here is the data set. So this is the one that you can download and try if this code works on your machine here. And if I open it, it's an Excel sheet that looks like this. Processing. It's a really small Excel sheet. This computer is just really, really slow. And it looks like this. It has only one data sheet, and it's player data. It has Major League Baseball players here. Their teams, their positions are already formatted as a data table. So it has those fancy like pull-down menus here if I enable the editing. And this is really slow. And it has the height, the weight, and the age of those players. And it has, I don't know how many, quite a few. If you go all the way down here, if it wasn't so slow, then I could actually go down there. It has 1,030, I guess, 4 different players. It's a little dated, so it's not the current roster of the Major League Baseball teams, but it's fun data set to work with. Okay, so if I open this in Excel here, let's go back to, that's my slide here. Then I get the first 6 rows. I use the head function here. Looks pretty good. It gets the first name, the last name, the team, the position, the height in inches, the weight in pounds, and the age. So it seems that it can read this Excel file. There's other packages that can do this as well. But then if you look at it more in detail, and I really like the str function, then we can look at what it found. It says, yes, I read something, it's a data frame, it has 1,034 observations, so those are the players, that seems right, I just checked in my Excel sheet. It has 7 variables, those are the columns, that's probably good too. And then it says my first column is first name, and it's a factor with 435 different levels. And it has those, and that might be fine. The last name, also factor, some text, that might be fine. Position, all those are fine, but if you look at the height and the weight and the age, then it gets kind of like weird, because I think the height and the weight and the age should be numbers, right? It should be like, I don't know, you have so many pounds. But what it says, no, it's factor, and factor is just R talking and saying it has something to do with text. So it read it as text, and that's probably bad if it's numbers, because I probably want to average them, and if it's text, how do I average text? And then it says, with quotation marks here, 67, 68. So what it really did is it took those things, they are numbers, but somehow it thought it's text and wrote it and read it as text. And now if I want to do any math with it, it's not going to work. So that's really bad. And I didn't really see this because text and numbers really look the same. I cannot really distinguish is this text or is this the number 210. So I really have to use this str function. Very, very important. Reading from Excel in R and lots of other tools is really a pain. The way to go probably is go into Excel, save whatever you want as a comma separate values file, open it in R, and you will not have those problems. But if you have the problems, you can fix them, because you can actually say, you know, this height in inches is really a character, but I want it to be numbers, so I can change the data type to numbers, and R knows. I look at the digits and put it together as a correct number, and I assign it back to the name. Also, the name was painful. It was height.inches. There were probably spaces in there, but data frames cannot have a space in there, so it replaces it with dots, makes those awful names. So you can assign it to the name that you like. You can delete columns by assigning nothing to it now. And after you do all this, then it looks better. It has real numbers here, it says numeric, real numbers for height, and real numbers for weight. But you really have to do this cleaning. So that's unfortunately painful. And once you have this, now you can say summary, and it will really figure out, you know, those are team names, so I count how many people are in each team, and those are real numbers, and I will give you the minimum, the maximum, and the things that the statistics that you really would like. And now you can do fancy things. If you say question mark aggregate, it will tell you there's an aggregate function that kind of does a like pivot table-ish thing on it. And what I says here, I would like to aggregate the age, the height, and the weight by the team, and it will give me, and I use the function me, and it will give me the team A and A. Anybody knows what team that is? That team, right? The average age is 29, the average height is 73, the average weight is 201. I have my rounding set really high here, but it will give you decimals on your machine for those, and for Arizona, Atlanta, and so forth. It will aggregate them by team. There is actually 40 teams, and I didn't have enough space, so I looked only at the head of this aggregation, so the first six teams. Okay, if you did this before you clean your data, it would like just say, I don't know how to aggregate the text 12 with the text 60 and so forth.
In the slide before that one, when changing from characters to numeric, why you put height.inches, y.pounds, and after age you didn't put anything?
It's because when we read the data here,
okay,
it somehow put those dots in there, and there was no dot here. So those dots happened when there was a space, and it fits in the Excel sheet what happens. The person that wrote the header for the height row wrote actually height, space, inches, and put an extra space there. You can see it,
okay.
But that's why there's this dot there. And lots of things you cannot see in Excel, but when you really look at the data, it looks messy, and that's what it is. Okay. Data to Excel. So this is probably what we write into Excel. This is probably what you maybe want to do if you want to create Excel sheets with R. This library, Excel SX, also lets you write style sheets. And what you do is you have a data frame, and you just say write Excel SX, and then the data frame, the name, and you need to give it a sheet name, because it's going to take the data frame, put it in one sheet. If you want to add a second sheet, you have to write append this through, and you can append as many sheets as you want in there, and it will take the data that you have in R and make Excel sheets if that's really important. Most people just write the R sheet as a CSV file and then read it, open it in Excel, because Excel can open CSV files as well. If we go back to CSV files are really easy in R to handle, because there's a function called write CSV. and read CSV, and it will just take a data frame, write it to a file, or read a file and give you back a data frame appropriately for that. Okay, so far so good. Let's now go to importing an Excel sheet, but with CSV. So what I suggest you really should do if you don't have to read like hundreds of Excel sheets, maybe it's like just 5 or so. You should go here, save file, save as, and then wherever I want to put it on the desktop, I guess, here, desktop. And then as the data type, you say here, CSV. And there's several versions. I think it probably doesn't really matter too much which you choose. And you say save. And now it saves this Excel sheet, this sheet here as a CSV file. You can still open it in Excel. It will not have all the colors and stuff. It will have just the text. But the good thing is in R, you can now just use read.csv and read it in. And what I did here is I went even a little more on the fancy side, because read CSV also allows you to read directly from a web URL. Let me go back here. So for example, if I do this and execute it, hopefully that works. And it will go to my website where this file lives. And if we go back to my website, where was the browser? I guess, no, not here. Here, so it lives here, and if you hold over it, it's unfortunately too small for you to see, but down here it says, there's a URL for that. If you open this URL directly with read CSV, it downloads the file for you and opens it. And now if I say head MLB, then you will see that it has here read from my website the data. And if you say still MLB, then you will see that it read those things not as text, but from a CSV. It has some smart way to figure out, hey, this is all numbers, this is probably not text. And it actually figured out those are all whole numbers, and only the H has decimals in there. So that's why it reads those. And again, if it's whole numbers, integers, or numeric, doesn't really matter. When you do math with it, it will figure out what the right way is to do is. So this is probably the way to go if you have only a couple spreadsheets that you have to work with. Okay, so far so good, 308. So I have a couple exercises again for you as your homework. So what you should be doing is you should read the cleaned MLB dataset. If you get to read the Excel sheet, that's fine. If you download the CSV file or use this link with reading the CSV file, that's fine. It's already clean. And then what you should be doing is you should look at the team Arizona. Do they have another name? What team is that?
Cardinals.
The Cardinals, right? So pick the Cardinals, all players from the Cardinals in there, and then you want to compare. So this is how you do it, and then you want to do some statistics, I guess, on this. How many players do you have in your data set from Arizona? So the way you would probably do is you would take this data frame, subset the rows from Arizona, and then count how many rows you have. And the number of rows you can get by using matrix functions like number of rows and rows. Then you want to look at who is the heaviest player in Arizona and find out who that is, what the weight is, and then you probably can look at the weight column and find the maximum right there. What is the average age of the players in the data set? So you probably pick the age column and say, I want the average or mean. You want to add a new column that's called BMI, body mass index, and want to calculate the body mass index of all the players. And on Wikipedia, you will see there's like underweight, normal weight, and overweight people. And you can check, are your favorite players overweight? Since we learned in the US, 60% of the population is overweight, right? So then at least a few of those players should be. But maybe they're not because they probably train all day, right? But are there underweight players in there? There's an interesting question that you could think about, like, are players that play different positions, have they different body mass indexes? I guess in American football, that probably would make sense, right? The people that need to be fast and run, they are probably like lighter than the people that are like just bulldozers and like whatever. hurting other people. So we want to do this for baseball. I have no idea. I don't know how baseball works, if there's a difference between different positions, but I imagine that there's people throwing balls and people running, and the running people probably cannot be overweight so much. And I see on TV there's people standing 3 hours around waiting for a ball, so they probably, I don't know, eat snacks the whole time and get fat. Okay, so this is what this is about. And then there's another exercise where you're supposed to create a data frame and save it as a CSV file and open it in Excel just so you kind of like practice getting the data in and out. Okay, so far so good. So this was already intense, and now we crank it up a level to more intensity, which is functions, loops, and apply, and we will at least get through the first few slides today. And the good thing is it only has 16, so that's nothing compared to what you went through. So the first thing is functions. We already used a whole bunch of functions because we already used, for example, the function mean, right, to calculate the average of a vector. And there's tons of built-in functions in R that are often based on ideas from statistics. There's everything that you want to do in statistics, right? You could do the mean, the minimum, the maximum, the mean, the median, quartiles, standard deviation, variance, correlation. You want to do rounding, and there's like 100 other things that statisticians want to do with numbers. And there's a function for that. If you want to do something, just Google R and whatever you want to do, and it's going to spit out what the name of the function is. Often they're very similar to the names that you have in Excel anyway, mean and max. Mean in Excel is called average, so there's slight differences, but not too much. Often what we want to do is want to sort things, and there's lots of sorting helpers there. You can sort a vector, you can find the order in a vector. That's basically saying which element, if I would sort it, would be the first element, which element would be the second one, and you get kind of the index of them. You can also reverse the order. You can get a rank, which tells you, if I would order them, which one is in rank 1, which one is in rank 2. Every time you want to use something like this, just say question mark, this name, and R will help you and give you examples of how to use that. And then there's all kinds of like random numbers, uniformly distributed one, normally distributed ones, and whatever the distribution is that you want or not want, you can create those. So here's an example. I create 10 randomly uniformly distributed numbers. By default, they're distributed between 0 and 1 uniformly. You can also change this by telling it I want them from -100 to +2000, if that's what you want. But here I get 10. And the numbers that I get are those, right? 0.113, and the last one, the 10th one, is 0.5. Then I can do things like this built-in function summary. It will give me the minimum, the maximum, the median, the mean, and quartiles. Do we think that this mean makes sense for what we just did? The mean is 0.49. If you randomly choose 10 numbers between 0 and 1 uniformly, then you think the average should be close to 0.5, right? Because half of the numbers will be smaller, half of the numbers will be larger. So the mean and the median should be around 0.5. It's only 10 numbers, so it's not really perfect. If you would change this to 1 million, you would see that those numbers will be almost exactly 0.5. Okay. Then we might want to sort them. And if you say sort X, it will just take the numbers, sort them from smallest to largest. Which is great because often we want to sort maybe a data frame by the age of the player or whatever you have for your Major League Baseball players. If you want to sort them in the opposite order, you just say decreasing is true, and we'll go then sort them from the highest to the lowest number. And this is probably enough for us to work with those. Now let's go one step further, which is user-defined functions, which is we implement our own functions. You probably will not need to do this too much, but you need to know how functions look like, because when we talk about apply and apply, you need to plug in a function. Okay, how do functions work? Well, they have several components. They have a name. You can choose it. It's a user-defined function. So I name my function int for increment. Then I assign to this name my function definition, and it always starts with a keyword function. And in parentheses, the arguments that this function accepts as the input. In this case, I say my input is only one vector called x. And then you have in the body that has those curly brackets what this function should be doing. My function is very simple. It should just add 1 to x. So I should write x plus 1. by definition in R, whatever the last thing is that's going to be executed or evaluated in this block will be my return value. So it will add 1 to x, and the result will be returned by this function. Okay, so far so good. If I look at my function inc, then it will write this function out for me. If I want to look at the mode of my function, it says this is a special object. It's of the data type function. It's not a number, it's a function. And if I call my function with value 5, it will say 6. Because it will take the 5, it will add 1 to 5. This will be my result, and so the result is 6. So that's pretty cool, pretty like tiny thing. Now the good thing in R is that whenever I use only vectorized operations here, so things that can work with vectors or other data types, then my function is automatically vectorized. And I can do things like increment 1 to 10, and it will basically take the vector 1 to 10 and increment each of the elements and give me back a vector with this operation vectorized done on all the elements. So that's pretty cool. But you can make it even more cool, and the example for more cool is down here. What if I give my increment function a matrix? It will say, I know how to add stuff to a matrix. I take each element in a matrix, add 1 to this element, and give you back a matrix. So the matrix that I make here is a matrix from 1 to 4, and I want to increment by 10. I will have to tell you how that works. And it will give me back a matrix applied with the same function. So that's cool because we can define a very simple function and can apply it then to a vector, a matrix, and it still works. Okay, let's talk about the top here, about the arguments. You can additionally have more arguments. For example, I make my increment function fancier because I don't want to increment maybe always by 1 every time. Sometimes I want to increment by other numbers. So I give it this extra parameter by. And I just change this +1 into +pi, and then it will just add whatever the value is that pi has here. And since I still want to use my code like increment 5, where I don't specify pi, I can give it a default value. So if somebody doesn't see me what pi is, by default, I will use 1. So still this increment 5 works, but if I say increment 1 through 5 by 10, it will actually do this. So that's pretty cool. If I give my function arguments names, then I can also change the order here. If I name them in my call, R will kind of like figure out, oh, the pi, you specified it first, but in the function it's after, not a problem, I can actually do this. Okay, and then you can do this also for matrices. So writing functions, very simple functions, is very easy. And it's actually incredibly useful, even if you do something simple like this that just adds 2 numbers together, because when you write code then later on, that's way better readable. When you say, oh, I know I want to increment this, I don't want to deal with like what I have to add and different data types. I just write this function and it's gonna work. Okay, and I want to stop today with this thing here, which is generic functions. And when we look at plotting, we will have to really think about this. And how those work is that in R, functions are often defined as a family of functions. And that's called a generic function. For example, the print function or the plot function. And then depending on what the actual class, the actual data type is that I give to this function, it might do different things. For example, the plot function might do something different to a vector than it does to a matrix than it does to a data frame. Because the visualization that you want to do for a vector might be different than what you want for a matrix or for a data frame. And this works because the print function and the plot functions are actually generic functions. And if you do things like this, there's a question mark print, plot, let's do this, plot. Then down here, we click enter. Then it says here plotting, but it says here generic XY plotting, and it says generic function for plot. And then it says there's actually a function that's called plot default that really does the plotting. And that's where we're gonna start up again next time after we talk about the exercises to figure out how those functions work. Then we go really quickly through loops, and then we'll do visualization. That's pretty simple. That's pretty easy because mostly it's just saying plot and what you want to plot. And we'll end up with making automatic reports in R and those like, what is it called, dashboards, right? Okay, that's it for today.